Last time we talked about the Diels-Alder reaction and kind of the controlled approach of the diene and the dienophile. So let's pick up with that topic. So the Diels-Alder reaction occurs by a controlled approach of the diene and dienophile. Okay, namely what we said was that if we had our diene and we consider just the two p orbitals at the end of the diene, we consider perspective drawing, that's going to interact with the monoalkene, the dienophile, such that the diene kind of swings in underneath and then sort of docks into the diene. And so this can again happen with heat or whatever. And we could even push arrows from this drawing. And that'll show the formation of these two new bonds. Now, I always like to have the dienophile coming in from underneath, but it could also come in from the top. So it could also approach, the dienophile could also approach the diene from the top. Okay, now what does that look like? Well, it's a similar picture, except what we have is just the dienophile coming in from the top. And so if we have our orbitals this way, I don't really like this picture as much. It's just sort of a preference of mine. And whoop, I even drew that one wrong because we want the bottom lobes to connect. Gosh, okay. Yeah, I'm really not used to drawing this one. But there is a point. Okay, it came in from the top as opposed to the bottom. Just doesn't look good. Okay, you have this. Okay, and here's your diene. This could relax to the same structure that we see usually, which is a cyclohexene. Anyway, the point is we could have the diene and the dienophile mixing and matching who's coming in from the top face and the bottom face of the other one. Now, what that means for you is that as a result, the Diels-Alder reaction will form both enantiomers of the product equally well. That is to say, you usually get a racemic mixture. Now, wait a second. Why are we talking about stereoisomers at all? So far, we haven't, I mean, the products that we've been drawing so far are achiral, right? Well, it turns out that if we add some more substituents, sorry, I didn't mean to just cut that off. If we add some more substituents, we can actually generate stereoisomers. For example, if we had this diene and this dienophile, we could form stereoisomers. Now, in a future lecture, we'll develop a model for predicting the stereoisomers. But in these three arrows, which shows the connection of the starred carbons with the squared carbons, we see that we have these two new bonds again. We've once again formed a six-membered ring with an alkene. Now, with these bonds, the stars and the squares are all stereoisomers. which means we have 4 stereocenters in the molecule, or four stereoisomers, jeepers, stereocenters. Which means we could form, well, 2 to the 4th power, so that's 16, right? 16 combinations of wedges and dashes because we don't have any symmetry in the molecule. Now, what we do know is that we form a racemic mixture. But what's cool is we form a racemic mixture of only one diastereomer. Now that's really impressive. For a reaction that not only forms carbon-carbon bonds, but to form one diastereomer for the most part, but let's just emphasize again, it's as a racemic mixture. And again, we'll develop this model over the next couple of lectures as we look at how we control the stereochemistry. Now, let's practice a few Diels-Alder reactions so we can start to see how the stereocenters are generated before we look at the complicated, well, it's not too complicated, just the model for predicting which diastereomer is major. So if we have our diene and our dienophile, I'm going to put that a little bit closer, sorry. The carbon atoms that are labeled with a star, these are the carbons that can result in stereocenters. That is to say, if you have something like this, we have a methyl group now. That methyl group, when it reacts with just a typical alkene in a Diels-Alder reaction, is now a stereocenter. If we attach that methyl group to the other positions, we would give rise to different Diels-Alder products also with stereochemistry at the center with the methyl group. In each case, I'm going to draw a 6-membered ring and then just attach the methyl group to the appropriate carbon. So let's put it also on the dienophile, and that's just going to move the methyl group over to this position. And so we have stereocenters at the various places that the methyl group was positioned around the ring, or around the forming ring, I should say. And I mean, some of these, in fact, are duplicates, but I just wanted to illustrate the point that it's when we put groups at that position that we get, that those 4 positions that we get stereocenters. So what about, and we could consider wedges and dashes then. Well, what about if we have the methyl group on the other, and let's add a second group like an ethyl group. What if we put these on the carbon atoms that are inside on the diene, the internal carbons of the dienophile? Well, after we do the Diels-Alder reaction, there's going to be a pi bond that moves between those 2 carbon atoms. And so we actually just have an alkene. An alkene can't have kind of RS or wedge dash configurations in this arrangement. So there's no kind of chirality to worry about here. So even though there are 6 carbons present in our basic Diels-Alder reaction, we only have to consider the 4 positions before we potentially forming stereocenters. Okay, so in the next lectures, we'll build the stereochemical model so that we can predict the major diastereomer that's formed in a Diels-Alder reaction.